We've already seen convolution methods for simulating from more complicated distributions via drawing from easier to simulate distributions and using our understanding or our knowledge of how different distributions are related to each other as a kind of why do this the hard way when there is an equivalent, much easier method. And we saw examples like with a binomial variable. So if I wanted to do this by working out each of the probability masses of a binomial and then working out the cumulative, I could do that. But particularly if this is n being large, so 17 flips of a coin, I don't really want to be working out what 17 choose 11 or 17 choose 14 is to get all of my coefficients. At least I don't want to do that when I've got a much simpler method which says, well, if I need to simulate 17 coin flips, simulating one coin flip is easy, and adding up 17 of those is easy as well. So I've got two easy steps instead of one hard step. Now, we used convolutions when I was summing a known number of variables. Now, what I was doing, I was adding, if I want to simulate a binomial with parameters n and p, from simulations of a Bernoulli with parameter p, I just add n of those. Sometimes we go the other way, and what we're doing is I want to know how many variables I sum until I reach some stopping criterion. So we actually did see previously an example of this, where a geometric random variable. I can think of a geometric random variable as being, for example, with coin flips, how many times did I flip the coin until I first saw heads? So heads first time would tell me the geometric is 1. Tails then heads would tell me the geometric is 2. Tails, tails, tails heads would tell me the geometric is 4. So in general, a geometric of parameter p could be obtained by simulating a whole load of Bernoullis with parameter p, not sorting the order, but just looking through and counting how many of those I need to look at until I see the next one as opposed to a 0. And that's an acceptance-rejection method, because I either accept the addition of one more or I don't. So a Poisson variable is closely related to the exponential variable with the same rate parameter. A Poisson variable describes how many events happen in a unit of time when the events happen independently of each other with expected rate lambda per unit time. The exponential variable gives the times between those events happening when they happen with the same rate, same expected rate of lambda per unit time. So I can actually simulate the exponential variables instead of simulating the Poisson. We saw in a previous video how to simulate from an exponential. It's a continuous distribution, but the interesting thing here is I can use continuous realizations to simulate a discrete outcome with the acceptance-rejection methods. Well, if I think back to the definitions, the exponential are the times between the arrivals. The number of those arrivals or events in a unit of time is the count, the Poisson count. Remember, Poisson's a count variable. It's 0, or it's 1, or it's 2, or it's 3. There's no upper limit, but it's got to be a non-negative integer. Because what I don't want to do is I don't want to be working out the cumulative probability of a Poisson variable, because adding e to the minus lambda to the 10 over 10 factorial plus e to the minus lambda to the 9 over 9 factorial plus e to the minus lambda. No, I don't hate myself enough to want to do that. So instead of simulating from a Poisson by working out all of those individual probability masses, I can simulate from an exponential. So I want realizations of a Poisson with rate parameter 4. I'm not going to do that. I'm going to simulate a load of exponentials with rate parameter 4. We saw in a previous video how to do that, involving the natural log of 1 minus a uniform point divided by the negative of the rate parameter. So I've done that already, and I've said that here I've generated 5. Maybe I'll need to do more, maybe I won't. 5 exponential variables, 0.0198, 0.4127, and so on. So if I think of this as a time between events scenario, the first event happened after time 0.0198. The next one happened at time 0.4127 after that. So if I add those up, 0.4325. So the fourth arrival happened after 0.0198 plus 0.4127 plus 0.2557 and so on. So the fourth arrival happened after 0.8089 units of time. And the fifth arrival happened after 1.2744 units of time. So what I have here is I know that if I have 1 unit of time, and a Poisson variable is a count of how many of these events happened in 1 unit of time. So the fourth arrival, or the fourth event, happened after 0.8089. The fifth arrival or event happened after 1.2744. Therefore, 4, and only 4, happened in a unit of time. I accept 4 of these variables, but not 5. So I can simulate the Poisson from the acceptance-rejection method without needing to go anywhere near those frankly awful probability masses for the Poisson. It's a much tidier way of doing the simulation based on my knowledge of how exponential variables and Poisson variables are related to each other.